on impedance functions, poles and zeros and their applications. We have already introduced the concept of impedance function as the ratio of voltage to current of a two-terminal network whose excitation is exponential, whose excitation is of the form e to the power st. The excitation could be either a voltage or a current, and we have defined that under this condition Z of s is the ratio of V by I with either V or I. One of them is an excitation, the other is a response of the form e to the power st. As an example, if we have well, one point that needs to be mentioned here and noticed by you is that when we speak of excitation as e to the st, we imply that the network under consideration, when we say excitation e to the st and the response is also e to the power st, we imply that the network under consideration is initially relaxed. Alright, when we calculate the impedance function, we don't take account of stored charges in inductors or stored energy in, stored charges in capacitors or stored energy in inductors. Alright. So Z of s, when we say V is exponential, I is also exponential, well, this is what it means. Now as an example, if I take a simple let's say RLC circuit, resistance, inductance and capacitance, a series circuit, then the if I, let's say, suppose I excite it by means of a current source I, which is I0 e to the power st, then you know that the voltage V across this shall be the sum of the voltages across R, across L and across C, and therefore V of V shall be equal to I0 e to the power st times R, this is the voltage drop across the resistance, plus L di dt, that is I0 s e to the power st, plus 1 by C. Now here is the question of initial relaxation. We are not taking into account any initial charges. We assume that there are no charges stored. Therefore, it is 1 by C integral I dt 0 to t, all right, and therefore this is simply this is simply equal to I0 e to the power st divided by sc. In other words, the impedance of the network between these two terminals is given simply by Z of s. If I take the ratio of V to I, which is Z of s is equal to R plus SL plus 1 over SC. As we shall see now, the impedance concept helps us to determine the so-called natural response of a circuit. We shall see later that the impedance concept also helps us in determining the forced response or the steady state response, as shall be demonstrated later. In the last lecture, at the last moment, we mentioned that there is an associated concept of admittance Y of s defined as the reciprocal of the impedance. In other words, the admittance of the series RLC circuit, for example, shall be 1 over R plus SL plus 1 over SC. They are very simply related. Y of s can be defined as the ratio of the current to voltage when the excitation of the two-terminal network is of the form of e to the power st with the network initially relaxed. That condition is important. All right. Now, let's take another example. Let's say we have a resistance, an inductance and a capacitance. These are the two terminals of the network, the resistance, inductance and capacitance. So the impedance, by looking at these terminals, it is usually denoted by an arrow. The impedance looking at these terminals is therefore given by R plus SL multiplied by 1 over SC. Combination rules are exactly those of resistances, SL plus 1 over SC, which I can write as, I can simplify this as R plus S squared LC plus 1, and here I shall have simply SL. I can simplify this further. Z of S is equal to R plus SL divided by S squared LC plus 1. I can write this as S squared LC plus 1, S squared LCR plus SL plus R. And this, it is usual to write such expressions. Obviously this expression is a rational function. It is a ratio of polynomials, two polynomials. It is usual to write the polynomials with the highest power term coefficiented to unity. That is, the coefficient of the highest power term is reduced to unity. Obviously that can be done if I take LCR out from the numerator and LC out from the denominator, and then I shall have R multiplied by S squared plus S, what shall I have here, 1 over CR plus 1 over LC, and here I shall have S squared plus 1 over LC. Is the term rational function familiar to you? Okay, a rational function is a ratio of polynomials, and a polynomial is a finite series with integral powers, integral positive powers. All right, a polynomial is a finite series with integral positive powers of the variable. All right, so I see that this can be written as some constant k, which in this case is R. Constant means it is independent of S. Then a polynomial in S, P of S, divided by a polynomial in S, Q of S. All right, so the impedance function is in general of this form, and you notice that the numerator and denominator both here are quadratics, that is, they are second order polynomials, and a second order polynomial shall have two roots. All right, both the numerator and denominator have two roots, and any polynomial can be written in terms of its roots as factors. All right, and this is one reason why the numerator here has been reduced to a form in which the coefficient of the highest power is unity, so that I can write this in terms of its factors. Suppose, if you write this particular rational function z of s as equal to r s squared plus s 1 by cr plus 1 over lc divided by s squared plus 1 over lc, you notice that the numerator roots, if I call them z1 and z2, small z, which I denote by a z with a slash in the middle. This is how I distinguish between cap z and small z. The roots of the numerator function are given by minus 1 over 2 cr plus minus square root of 1 by 2 cr whole squared minus 1 over lc. Is that okay? All right. These are the two roots of the numerator, and let us say the denominator roots of the denominator polynomial are denoted by p12, small p12. Then you see these are purely imaginary, that is, it would be plus minus j 1 over square root of lc. The roots of the numerator can be either real or complex. Can they be imaginary? Yes, they can also be purely imaginary, but if that is so, purely imaginary under what condition? Capital R? Capital R is infinity. Did I make a mistake somewhere? No, this is okay. Pardon me?
When L is less than 4 CR square.
Purely imaginary.
Purely imaginary. Okay, if it is purely imaginary, then you see it's identically equal to 1. Don't you see the function would be identically equal to 1 because this term will drop out. Capital R infinity means S square plus 1 by LC and S square plus 1 by LC. So you are left with only a capital R. This becomes a degenerate case. Let's not worry about it. What I am saying is that the numerator roots can be either real or complex. Alright. The denominator roots are purely imaginary. Alright. Suppose this quantity, the quantity under the square root sign, suppose this is greater than 0, then obviously both the roots shall be Z12 shall be real and negative. Alright. Now these are indicated on the complex plane or the S plane like this, sigma j omega, and the two roots of the numerator are denoted by circles. Suppose they are negative, then there will be one will be here and one will be here. They are indicated by small circles, and the roots of the denominator are indicated by crosses. They shall be on the imaginary axis, purely imaginary. This is the S plane on which the roots of the numerator and denominator are indicated, are plotted. You notice that the original expression Z of S can now be written in terms of its roots like this: S minus Z1 times S minus Z2 and S minus P1 multiplied by S minus P2. Alright. The original expression can be written like this, and this is the reason why the highest power coefficient was reduced to unity. Alright. And it is obvious that when S takes the value either Z1 or Z2, the expression becomes a 0. Z of S becomes 0. When S takes a value Z1, S equals to Z1, Z of S becomes equal to 0. When S takes a value Z2, Z of S becomes a 0. And therefore Z1 and Z2 are called the zeros of the impedance function. Z1 and Z2 are called zeros of the impedance function. And that's why we use the symbol small z for zeros. On the other hand, when S takes a value P1 or P2, the impedance function becomes infinite, it blows up. Alright. Such values of S for which the impedance function becomes infinity are called the poles of the impedance function. P1 and P2 are poles, and therefore this diagram that we have drawn here is called a pole zero sketch or pole zero diagram. Pole zero diagram. Alright. Let's take another case. Is there any question on this? Definition of poles and zeros are, let me repeat, if you write Z of S as equal to k times in general, it is not necessary that the degrees be 2, they could be higher than 2. It is not necessary that the degrees of the numerator and denominator be equal. It is not necessary. Alright. For example, if you take, let's say, the simple RLC network, alright, two terminal network, then you know the impedance is R plus SL plus 1 over SC, and this can be written as 1 over SC S squared LC plus SCR plus 1, which I can write as L, LC taken out and C taken out from here, S, then we have S squared plus CR by LC S R by L plus 1 over LC, and you notice that the numerator is of degree 2 and the denominator is of degree 1. All right. So the two degrees can be different. Now the numerator has therefore two roots. The denominator has only one root. Where are these roots? The denominator root, where is it? It's at the origin. So there is a single pole at the origin, and if the roots of the numerator are, let's say, complex, then we shall have two zeros like this. You also notice that if the roots are complex, then they are complex conjugates. That means if I have minus a plus jb as one of the roots, then the other root must be minus a minus jb. Now why is that? Why is this constraint?
Because the coefficients are real.
Because the coefficients are all real, all right, and therefore it is a property of real coefficient polynomials that if there is a complex root, its conjugate must also be a root. Now you notice that the point that I was making is that the numerator and denominator degrees, P and Q degrees, need not necessarily be the same. They may be different, and therefore the number of poles and the number of zeros may be different. Here, for example, at s equal to 0, the impedance function blows up. It becomes infinity. That is, it allows no current to flow. S equal to 0 means what? E to the st, s equal to 0 means a constant, which means a DC. And obviously this is corroborated by physical considerations that the capacitor does not allow a DC to pass. All right. Okay. Then the two zeros here may be complex, may be real and negative. All right. And at a zero, the function becomes 0, which means that the total circuit acts as a short circuit for that particular value of s, not for any other value of s. We are going to take another example. Let's take that example. Before we generalize this, let's take an example. Let's say we have a resistance R1, a resistance R2, and let's say a capacitor C. The impedance function between these 2 points obviously is given by R1 plus R2 divided by SCR2 plus 1. Does that sound magical? No. What I have done is R2 1 over SC divided by R2 plus 1 over SC, and this is what I have simplified to this. Okay, I avoided that algebra. So I can write this as SCR2 plus 1, SCR1 R2 plus R1 plus R2, and now I must reduce it to that form, that is, the coefficients of the highest powers should be 1, and so I take CR1 R2 out and CR2 out, therefore I get R1, and the denominator I get S plus 1 over CR2, and in the numerator I get S plus R1 plus R2 divided by C R1 R2. Is that okay? Alright, we can write this in a in a more elegant form. Yes. You couldn't see the previous one? Okay. S plus R1 plus R2 divided by CR1 R2 and S plus 1 by CR2. Now you notice that R1 R2 divided by R1 plus R2 is the equivalent resistance of R1 and R2 in parallel, and therefore I can write it in a somewhat more decent form as R1 S plus 1 over CR2 S plus 1 over C R1 parallel R2. Let's call this R1 S minus P1 there is only one pole, S minus Z1, there is only one 0. Then Z1 is equal to minus 1 over C R1 parallel R2, and P1 is equal to minus 1 over C R2. So both the roots of the numerator and denominator, all of them are real and negative, and therefore the pole 0 sketch shall be like this, sigma j omega. Now if I go from 0 to the left, what shall I meet first, the pole or the 0? It has to be a unique answer. The pole. So they cross and then the 0. This would be minus 1 over C R2, and this would be minus 1 over C R1 parallel R2. Or I say this is minus P1 and this is minus Z1. This is the pole 0 sketch.
So shouldn't it be just P1 and Z1? Yes, sir. P1 and
That's what I do.
put the minus sign there.
Thank you. This is P1 and this is Z1. Absolutely right. Okay, now listen to me carefully. I am going to make what I defined here as poles and zeros were purely mathematical convenience. We said Z of S is a rational function. So I find out the roots of the numerator, roots of the denominator. I call the roots of the numerator as zeros and the roots of the denominator as poles. All right. So what is the physical interpretation of a pole or a zero? One of the interpretations is that at a pole the impedance becomes open circuit. At a pole the impedance becomes infinity, it becomes an open circuit, so it does not allow a current to flow. Agreed? On the other hand, at a zero the impedance becomes a short circuit, so it does not allow any voltage to be dropped. Agreed? They are completely duals of each other. We can make the same kind of interpretation with regard to an admittance. After all, admittance zeros are impedance poles. Isn't that clear? Because one is the reciprocal of the other. So I can make the same kind of interpretation. Now another physical interpretation can be like this. It's the same thing, but we will state in different terms, and this is what will lead to application of the pole zero concept in finding the response, natural response of circuits. You see, V equals to Zi provided V or I is exponential. All right, this is the definition. Now you notice that if Z equal to 0, if Z equal to 0 at some value of S, then V equals to 0 irrespective of I. Isn't that right? Okay, is that clear? This is a simple mathematical statement that if Z equals to 0, whatever I is, it doesn't matter, the product shall be 0. So V equal to 0 irrespective of I, which means that a current can exist without a voltage. Agreed? A current can exist without an external voltage. At this value of S, a current can exist without an external voltage, which means, well, if for a current to flow, there must be charges available. Current, after all, is the flow of charge, which means that if a current has to flow, well, it must be due to internally stored energy. Agree? And therefore a zero is in some way related to the natural response of a circuit. The zero is in some way related to the natural response. What response? Current response. Natural current response of a circuit. And precisely if you think, if you ponder a little, you see that if Z of S1, some value of S, if Z of S1 is equal to 0, then S1 is one of the roots or one of the functions occurring in the exponential of the natural response, which means that if g of S1 is equal to 0, then the natural current response of the circuit should include a term of the form I1 e to the S1t. I shall illustrate this in a moment, but let the concept soak in. The concept is that we start from this relation and we say that if g is 0 at some value of s, then that s must have some relation to the natural response of a circuit. And we have seen in the examples that we have worked out that the natural response is of the form of e to the st. Natural response, for example, for a second order circuit, it was a1 e to the s1t plus a2 e to the s2t. How did that e to the st come? Because we converted all equations into a homogeneous differential equation and we sought the solution in the form of e to the st. Agreed? And therefore, the impedance concept therefore gives us the values of s which shall occur in the natural current response of a circuit. Let me illustrate this. Yes.
Sir, how z is equal to 0 is related to natural response of the circuit?
How z equals to 0? Okay, this is what I had explained. If z equals to 0, then from this relation we see that V is equal to 0 irrespective of I. In other words, even without the presence of a voltage, a current can flow. Now, without any external voltage, a current can flow if it is the natural response. If there is internally stored energy. And therefore, conceptually it appears that this must be related to the natural current response. And S, the value of S at which the function becomes 0 should occur in the natural current response of a circuit. And S occurs as a power of E, alright, S and T, the product occurs as a power of E. And what is the dimension of S1? It is a frequency, and therefore S1, the value of S at which the impedance is 0, is called the natural frequency of current response, natural frequency of current response. And in that sense, the zeros identify the natural frequencies of current response. The zeros of an impedance function identify the natural current response of a circuit. Yes?
Sir, if z is 0 and we apply some voltage,
Hmm.
then will the circuit burn out?
Will the circuit burn out? Yes, the current shall be infinity. The current shall be infinity. But then you have to generate a voltage of the form e to the power s1t. Okay, those questions we shall take up later. Conceptually, a zero of an impedance function, the function becomes 0. Yes, Aditya.
So you had said that the impedance concept, we assume them the inductor or the capacitors to be relaxed.
Yes. In calculating the impedance, just to I understand your question. In calculating the impedance, we say it is the ratio of voltage to current. And this voltage or current is an external excitation. When you apply that, all elements must be relaxed. Because otherwise, you see, the current response would not be purely e to the st. It might have a constant component also. Alright. So what we are doing is, in calculating the impedance, you see, one has effect on the other. In calculating the impedance, we assume the circuit to be relaxed. Once we calculate that, then the parameters of the impedance are this constant K. I'm sorry, let me write it again. This constant K and the coefficients of P and Q. These are the parameters of the impedance. Alternatively, we said that P and Q, let them be factored out. Then these factors or the roots, what is their physical interpretation? This is what we are looking into. The physical interpretation is that the roots of P of S identify the natural frequencies of current response. Identify. It has nothing to do with whether charge is stored or not. If you wish to find the natural response of a circuit, Z1, Z2, Z3 and so on, which are the roots of P of S, shall show their teeth, shall show their face. Let me take a very simple example which might convince you that it is so. Let's take the familiar RLC circuit. Well, the impedance is Z of S is R plus SL plus 1 over SC, which is equal to SC S squared LC plus SCR plus 1. All right. Now, we wrote this as L multiplied by S squared plus what was that? R by L, S R by L plus 1 over LC divided by S. Now you put this equal to 0, which means that the numerator, that is S squared plus S R by L plus 1 over LC equal to 0. Don't you see that this is precisely the characteristic equation of the circuit? If you write the differential equation and try a solution of e to the st, this is what we had got earlier, and it is the roots of this S12 in terms of which we express the natural response as e to the S1t plus A2 e to the S2t. Agreed? So S1 and S2 are indeed the natural frequencies of the current response. Agreed? This simple example demonstrates that what we are saying is correct. Let's take an example. Suppose I have a resistance, let's say 2 ohms, another resistance 4, and a capacitance of value 1/4 farad. We assume the circuit to be initially relaxed. We are calculating the impedance Z of S. Obviously this is 2 plus 4 multiplied by, yes, the impedance of 4 by S, that is correct, divided by 4 plus 4 by S. I simplify this, 2 plus 16 divided by 4S plus 4. Is that okay? I multiply by S, so 16 divided by 4S plus 4, which I can write as 2 plus S plus 1 and here 4. This I can write as S plus 1. Let me make it into a rational function. 2S plus 2 plus 4. So 2S plus 6. And I write this as 2S plus 3 divided by S plus 1. Alright. Therefore, the pole 0 diagram is sigma j omega. The pole is at -1, and the 0 is at -3. No, I'm sorry, this should be a circle. The 0 is at -3. Alright. Now, what we are saying is, we have identified the 0, and if we wish to find the current response, natural current response of the circuit, then e to the -3t shall appear in the natural current response. Let us see now how can you obtain a current without having an initially stored energy. Therefore, let us say that in this circuit 2, 4, let us say that in this circuit 1/4 farad, let us say that V sub C 0 minus, let us say, is equal to V0. Suppose V sub C 0 minus is equal to V0. And then what we do is, between these 2 points we have measured the impedance, we put a switch on at t equal to 0. And I wish to find the current through this short circuit. You see, remember that V equal to Zi, what did we argue? We argued that if Z equal to 0, then I can exist without an applied voltage. Okay? It is between these 2 points that we considered V and I. We considered V between these 2 points. So let me make V equal to 0. What does it mean? It means that I short circuit this. And let's say this is the current I. Then without doing any differential equation, I can say that I must be of the form sum I1 e to the power minus 3t. Alright? To find I1 we have to apply an initial condition. What is the initial condition? I1 at t equal to 0, at t equal to 0, the current I, now I need an initial condition on I of 0 plus, after the switch is closed, obviously is V0. I didn't say what is V0. Minus V0 by 2. That is correct. Because the voltage from here to here becomes V0. Current is in this direction, assumed. So it must be minus V0 by 2, which means that this is equal to I1, and therefore I is equal to minus V0 by 2 e to the power minus 3t. I have not solved any differential equation. I have simply found out the zeros of the impedance between these 2 points, and then what I have done is I have shorted them, shorted the 2 points, found out the current through this, and I suspect that e to the minus 3t, well, I am convinced that e to the minus 3t shall occur in the natural response, natural current response. We will come to voltage a little later. Natural current response, and therefore this must be the total solution. For example, instead of the voltage, instead of this current, suppose I had to find out VCT, then I can write it immediately as the initial voltage is V0, so it would be V0 e to the power minus 3t. Or I can find out the current through the capacitor, I sub C. Well, I sub CT would be 1/4 C times dVc dt. Is that clear? Okay, let's let's consider the other case in which we have to interpret the poles. Physical interpretation of the poles. Physical interpretation of zeros is, let me repeat, that you measure the impedance between 2 terminals, alright. If you short circuit these 2 terminals, that is, if you make the applied voltage equal to 0, and there is initial stored energy somewhere in the circuit, then the current response shall contain the frequencies that are identified by the zeros of the impedance function. Alright. Let's see the other case, namely the poles. For the poles of an impedance function, poles of Z of S, we work in terms of admittance instead of impedance. These are zeros of capital Y of S. Capital Y conventionally is the symbol for admittance, alright, and V equal to Zi can be written as I equal to YV, and we argue the same thing, that is, if Y S1 equal to 0, some value of S at which the admittance is 0, then S1 must be a pole of Z, alright. A 0 of Y is a pole of Z, because one is the reciprocal of the other. If YS1 is equal to 0, then I equal to 0 and V is arbitrary. Any V would do. There is no restriction on V, which means that without a current excitation, a voltage can exist, alright. Without a current excitation, a voltage can exist. So this value of S1 must be related to the natural voltage response of the circuit. Natural voltage response of the circuit. In other words, the voltage response must be of the form, must have a component V1 e to the power S1t. The voltage response V of t must have this particular component. Alright, let's take another example to illustrate this point, that is the interpretation of poles. I repeat, zeros are associated with the natural current response and poles are associated with natural voltage response. These are new concepts, and I would go very slow, and I want these concepts to soak in, because in later classes we will simply assume, we will not explain why we are doing this. We will simply find out the pole zeros and say this is the voltage response, this is the current response, and so on. Let us take an example to illustrate this point, that is interpretation of poles. The same example we take, R1 equal to 2 ohms. Please follow this carefully. R2 is 4 ohms and C is, let us say, 1/4 farad. And we have a situation like this. Let us say we have a switch. Now what we have to do is, without a current excitation, voltage can exist. That means we will have to open the switch. A current source has internal resistance of infinity, and therefore we will have to open it. Okay? So this is opened at t equal to 0, and there is a source. There is a source, let us say current source here. Okay? Between these 2 points, let us say A and B, the impedance we have already found out, Z of S is 2 times S plus 3 divided by S plus 1, or Y of S is half S plus 1 divided by S plus 3. So the 0 of Y is at S equal to minus 1. Now when this current source is here, the capacitor accumulates a voltage. Alright, the capacitor accumulates a voltage because the current passes like this and it charges the capacitor. Alright, suppose at t equal to 0 minus, Vc 0 minus, suppose the capacitor accumulates a voltage of V0. Now the switch is thrown open. What you have to find out is VAB for t greater than equal to 0 plus. Obviously this would be, it must contain a term e to the minus t and some constant. That constant obviously by inspection is V0. Alright, because when you open it there is no drop in this, so it must be the voltage across R2, which is the same as the voltage across C. Is this point clear? Now let me generalize now. Let me generalize. What you do is, you take a 2-terminal network, and between these 2 points you measure or you calculate the impedance or admittance. Let the impedance be of the form K P of S divided by Q of S, which I can write as K. I can factor this out. You remember how K was taken. K is taken out such that P of S has the highest power coefficient as unity, Q of S is the highest power coefficient as unity. Alright. Then suppose the degree of P be equal to M. This is how we write the degree of a polynomial, just like temperature. Okay. Suppose the degree of Q is equal to M, then M and N need not necessarily be the same, they can be different. If it is so, then a polynomial of degree M can always be written as the product. Are you acquainted with this symbol? Yes. Okay. The product of factors like this, S minus Zi, where I goes from 1 to M. Similarly, in the denominator we shall have product of factors like S minus Pi, where I goes from 1 to N. Okay. Next, if you wish to find out the current flowing through the short circuit, that is, if you short circuit these 2 terminals, and if you want to find out the natural current response, then the natural current response I of t shall be of the form Ai e to the power Zi t, where I equals to 1 to M. Is that clear? Due to internal stored energy, if you wish to find out the current when these two terminals are short circuited, then the current response shall be of this form.
So, but here Z of pi must not be repeated
Yes, that we shall come a little later. If there are repeated roots, then we shall have to modify in the same manner that we did for differential equations. That is, instead of let's say Z1 and Z2 are equal, then instead of taking A1 e to the Z1t and A2 e to the Z2t, we take A1 plus A2t multiplied by e to the power Z1. It's the same kind of modification. On the other hand, if these terminals are left open, then the natural voltage response across the terminals shall be given by Vt equal to summation Bi e to the power Pit, that is, the poles shall now show their teeth. The poles determine the natural frequencies of voltage response where I equals to 1 to n. All right? And then these constants have to be evaluated from initial conditions. We shall consider several examples next time to illustrate this point. And that's where we conclude today.